बिस- बिस्मिल्लाहिर्रहमानिर्रहीम रब्बी इश्रह ली सदरी व यस्सिर ली अमरी वाहलुल उक़दतन मिन लिसानी यफ़क़हू क़ौली. In the name of Allah, the most merciful and the beneficent. We continue with this our topic of knowing the characteristic of material that will be used for construction of a flexible pavement. Not only construction, but for the design of flexible pavement. Uh, Actually, knowing this property will help in designing a pavement uh, and making sure that whatever the material is specified will result in a long-lasting pavement. So, today in this lecture, we will talk about the base and subbase materials and the asphalt mixture properties. And these are very important for design of a pavement, as I've said. So to start with, first we go with aggregate basis and subbases. Um, in order to get this base and subbase material, uh, normally we use crushed or query process aggregate because of its availability, its construction and good performance. And the countries like Pakistan, we have abundance of those materials. But we can use some recycled material from the building demolished and demolished waste, or from any other, even from the existing structure. But I feel that we have to process a lot. Sometimes people have to realize that the initial cost for getting those material at par with the natural material uh, is more. And together with that, we also have to compromise on uh, some of the properties of a natural material. So though with sustainability issues in the world, uh, people are using recycled aggregate, but in the countries like ours, I feel it is my understanding that we still, for us, a natural material is more reliable as well as more readily available. So if you don't have a crushed material, we have another source, what we call a natural occurring gravel, but we must know its proper gradation requirement. The maximum size of the aggregate depends upon the size of the project and the size of the compaction being used. Um, Another thing is about the gradation. The S curve we normally used for gradation of highway materials, and this is in order to have a better compaction and adequate compaction. It is very necessary to have a proper gradation of material. If you have a smaller projects, we can have an aggregate graded down from 3 by 4 inches in size. Talking about the gradation, if we are using the dense gradation or open gradation, crush aggregates, uh, this dense, each of it has the advantage. Though dense graded give you a stronger material on pervious well, but with open graded material, you can have a problem. You can solve the problem of drainage. We continue with this our discussion. Now, if I said it will gradate, but we have to provide a sand setting bed and a geotextile to prevent sand from filtering into the base. For a residential pedestrian application, Sand base can be used with when the subgrade is compacted or bearing on undisturbed earth and in area where frost heavy is not a constitution. So sand can be clean and free of deleterious material. Salts in the sand will often wick through the break, showing efflorescences on the surface. Normally, the minimum thickness for aggregate base depend upon the strength of the subgrade, but generally a 4-inch is always recommended. This is a flexible base of properly graded crushed stones. Now, if you are talking about a reinforced concrete or um, a lean concrete, it is 4-inch is enough, depending upon what type of subgrade we have. But normally, if you have a subgrade of say CBR 10, it's very safe to use that 4 inches aggregate, 4 inches thickness of a base. And we also required not only sub base, but we also required a sub base, and this will help you reduction in the thickness of all type of bases as well as provide better granular material for drainage purpose. Normally, there are two types of aggregate. We say we can have a treated aggregate and we have an untreated aggregate. So if you look at this untreated aggregate, the property you are going to specify based on CBR is for subbase you have a minimum of 20 CBR. For base it is 80. In Pakistan we have a base of around 90 to 95. The liquid limit, though we do not specify, but normally if you recommend it is 80 base or 75 base, that's a very good material. The liquid limit is also important and it is limited to maximum of 25 for both of them. We do require non-plastic base, though for sub base 6 is the limit. Obviously, in order to know the properties of sand that can be used as an aggregate, as a fine aggregate, we have to do the sand equivalent test, and that is 25 for sub base and 35 for base. Also, we must know how much the final material will have. Some material, if passing number 2, maximum passing number 200 C, or we call minus 200 C, that should be 12 for sub bases and 7 for bases. We have discussed a lot in our previous lecture about the resilient modulus of subgrade soil. The modulus of the bases and subbases can also we can also know, though we don't have a explicit equation like MR is equal to 255 CBR power 0.64, but we do have this this chart in which you can, if you know the CBR, just draw perpendicular and you will get the modulus. For instance, if I say we use CBR of base 70, the corresponding resilient modulus or modulus value is between 25 and 30. So this is how you can correlate. Just draw like this. Just draw a line perpendicular to 70 and you will get the corresponding modulus value. Another thing we need when you are designing an ASHTO pavement design, using an ASHTO method for flexible pavement, you also need structural layer coefficient. This I will discuss when we discuss pavement design. But if you want to know the the value of, interested in knowing the value of layer coefficient, so just extend this line and around 0.13 you can use for layer coefficient. This is for untreated base. What about the treated base? Now, If it is a semi-treated base, you must know the unconfined compressive strength of the soil, of the base. And this, if once you know this thing, say 600, you have a modulus of uh, elasticity modulus of 7 to 10 power 5, or for say you have a 400 compressive strength, you can have this 6 to 10 power 5. 6 like I can say. If you have a bituminous static base, then obviously you can have some Marshall stability value, say 1000. And for that you have around 20,000, so 2 lakhs or 200,000 this and the level of this. Now, what is the difference between, for those of you who want to know what is the difference between untreated and bituminous treated, or any treated material? You know, when we talk about untreated means whatever the crush aggregate we have, we laid it, compacted to required density. But in case of uh, treated base, before having another layer of surface course, we must add either bitumen or cement with an aggregate. What does it will do? What will do? It will then create uh, the harder material, or it can improve upon the modulus of the base, and consequent upon which it will have smaller thicknesses of surfaces, asphalt surface courses. People in developed countries now used the treated base. They don't use untreated base. Uh, and obviously, as you can see that, if you have a very good material, say of CBR 30, CBR 100 even, you have a 30,000 modulus PSI. But if you can see that uh, if uh, if you just use either a bituminous treated base or semi-treated base, this is enhanced by 10%. So when you were talking about when for untreated base, we're talking about uh, say thousands or 10,000s, but here we are talking about 100,000s. So 10 times the modulus of the base material will increase, and it will obviously will have a better pavement, better base material. Now, this as I was saying that we call this treated base asphalt treated as asphalt base as well. We can use this for brick paving, but if you want to have a brick road, you can do it. So that's but before doing this brick paving, we have to repair those cracks before the installation of the base, and we have to install some membrane to strengthen the pavement and prevent the setting wet shifting from through cracks in the pavement, in the asphalt surface. We were talking about base. Now uh, there is a chart available for estimating the resultant matrix of subbases as well. The same way applied, I said that we can use CBR 20. We can, for CBR 20, we can have this modulus value of around 13,000 psi. And we can also have a CBR 30 material, then obviously it will be around 15,000 psi, and consequently the value of the structural error coefficient will be enhanced. So that's that's for the bases and sub-bases. Now we move on. The asphalt binder characterization you can see, as well as we talk about the asphalt bases. Now, if you look at this asphalt HMA performance characteristics, need physical test that characterize HMA performance that may change throughout the life of the pavement. Normally, what we need to understand that the HMA must be good enough to against the rutting. This is a key performance parameters, and all it depends highly on the HMA mix design, though it also depends upon the external loading and the temperature variation. So for the sake of material characterization, we want to make it sure that whatever mix we are using, it's adequately designed and adequately specified and adequately evaluated so that no fault of material input in the pavement design could result in the failure of the pavement. We also know that the pavement also fail. One of the major um, destructing factor is the alligator cracking, or what we call the fatigue life, and that has to also be measured in the and has to be adequately designed, and it should be noted that the mix design uh, is good enough to have adequate HMA life because of its material. Then there is a low temperature cracking. For there, we need some tensile strength testing. The stiffness is a very important property of a material, especially those material that are being used as a structural material. This HMA stress strain relationship is we characterize the stiffness of this HMA by using elastic or resilient modulus. Although the elastic modulus of various HMA types is rather well defined, this can be determined how elastic and resilient modulus varies with temperature. Also, many deformation resistance can also determine elastic or resilient modulus of an HMA that will be used. Our pavement also fail because of the moisture. So we need to test our pavement mixture against moisture as well. So there are certain combination of aggregates and asphalt binders that can be susceptible to moisture damage. This surface deformation resistant tensile strength can also be used to evaluate the moisture susceptibility of HMA mixture. Now, if we don't have anything without doing a test, we can always know the modulus value. Normally, we test our material for Marshall stability. So if you know our Marshall stability, say 2200 pound or 2200 pound, we can always estimate the modulus value. Okay, so what we do, if you know the Marshall stability, say for a Marshall stability of normally we have the minimum requirement of 1000 kg. So if we have this around 22,000 pound, we can use this 4.5 into 10 power 5 modulus. And obviously, if we project our modulus, this will be, and we'll project this modulus will around 0.44 that we always use in the design of our structural pavement in Pakistan. Similarly, for the base course, we do is this for the base course, if you use this margin stability of around again 1000, we can have this layer coefficient uh, of 0.35 and the modulus is around 400,000 psi. So this is without testing and without knowing or without just performing the Marshall stability test that we use for our job mix formula for knowing the optimum asphalt content of a our paving mix. We can estimate the values for our wearing course as well as a asphaltic base course. But what about the actual values of um, our modulus? This can of late with the super pave test protocols, people have come up different ways of measuring the modulus of an modulus of elasticity modulus of an asphalt concrete. One is the dynamic complex modulus. It's apply a repeated load at varying frequencies, test a specimen over a relatively short period of time, and measure the specimen recoverable strain and the permanent deformations. Some dynamic modulus tests are also used to able to measure the lag between the peak applied stress and the peak resulting strain, which provides insight into a material viscous properties. Test results correlates reasonably well within service payment, setting measurement, but test is somewhat involved and difficult to run. The difference between a resilient modulus test and a complex test is that the former uses in a resilient modulus we have uh, with a given we have a waveform of sine with a given test period, while the later applies a sinusoidal or hypersine loading with no rest period. One of the methods for describing the stress relation sample is this is which we have in order to calculate next elasticity modulus. We use stress over strain, where sigma naught is maximum dynamic stress and E naught is a peak recoverable axial strain. Axial strain. Asphalt, like we know, is a elastic plastic material, and it's not a perfect elastic material. So likewise, when we were discussing the reservoir modulus of soil, we say we are talking about the stress over recoverable strains. So is the case with testing an HMA asphalt as well, hot mix asphalt. This is the this is the dynamic modulus test setup in which the sample is prepared and we have all those setup and then loading, and we apply those loading through the same procedure but with a different setup. Explaining this dynamic modulus obviously is beyond the limit of this course. So that's why I'm just limiting myself to just a pictorial demonstration of what actually happened. Another way to know the elasticity modulus is to calculate its stiffness modulus. How? Stiffness modulus is a fundamental property of fatigue evaluation in asphalt concrete. Here we have to be, very mindful the difference between what we get from dynamic modulus and what we get dynamic stiffness. The main difference when we talk about dynamic modulus test is dynamic modulus test is what is we mean that when perform dynamic modulus test, we have measured, we have made it show that our rating resistance is get form. And in order to get our fatigue resistance measurement, we use this dynamic stiffness test. It's a very simple 2-point loading test as we use ordinary for our testing our concrete beam. So this is a fundamental parameter. This is stiffness modulus, and it is based on the resident deformation of the beam at the 200 repetition, and this is also known as dynamic stiffness modulus. The load is applied with the Haber-Sein loading with a load duration of 0.1 second, and we have a rest 0.4 seconds like this, and then applied to the third point. The 3-point point, the asphalt beam is prepared, asphalt HMA beam is prepared. We have a simply supported roller supported, supports, and we applied loading to 1/3 point, that is L by 3 for any beam sample, and this L is normally 12 inches. The width of the beam is 1.5 to 3 inches, and the height is 15 inches. Some formulation to calculate the stresses. Just you need this load, the point of the application of the load, your cross-sectional area of the beam. Once you know that thing, you can also, you are also measuring the deflection. So you can also know the stiffness modulus just using this equation. And all those other parameters like a PA, L, and delta, PHQ is already defined. And you can always have the, you can also evaluate the tensile strain using this relation. Now, this is an example calculation from your book in which we have been given that a beam with a span length of 12 inches and a width and depth of 3 inches is subjected to dynamic load of 300 pounds at third points. The dynamic deflection measured is 6.25 into 10 power minus 4. We have to determine the extreme fiber stresses and stiffness modulus by using the equation in the book that are 7.12 and 7.13. And in order to apply this equation, a Poisson ratio of 0.35 may be used. So this is a very simple solution. For example, of the parameter we need to know strain fiber stress. This is the input, this is the formulation, and we got this value. Similarly, to know the stiffness modulus, we apply this formula. These are the input, and we get this. And if you want to know shear modulus through, higher HR, it depends upon the depth to the length ratio. And for that, if you have a depth of say 1.5 inches, then you can have you have to use 1.1 sector for say for 3 inches depth. Normally we use have 1.5 inches, but for this case, if we have a height of beam is 3 inches, then we can just have to multiply this correlation, the value calculated above by the correction factor, which is 1.16. Now, if you don't want to use classically, people use this nomograph to calculate the modulus of the mixture. Again, this is based on knowing performing some classical test on an asphalt material that is always a requirement for specifying any bituminous binder. So these are what we call a shell nomographs or shell charts. In order to use this shell chart, we just have to know this value of penetration index, and it is dependent upon the penetration of the test penetration values of an asphalt that is being used, as well as the ring and walls temperature. This was developed in 1978, and this this problem will give you the how this shell is this used. So we have been given an asphalt cement as a penetration of 22 and a ring and ball point of 64 degrees centigrade. We have to determine the stiffness modulus under temperature of 11 degrees centigrade and a loading time of 0.02 seconds. So first of all, we have to calculate the value of A, and we use that value of A, we use PI as we were discussing. These A and PIs are all we required for using the nomographs. So we have calculated this, and how we use this chart is first we'll calculate the stiffness modulus of bitumen, and then we'll use this value to calculate the stiffness modulus of a mixture. Let me show how you can done is, you see, this is a type of loading that is given to you, and then is a temperature difference. You just want to you connect this time of loading and you proceed like this. And here we have a penetration index that we have calculated. And once you project this line, will meet at some line. And in order to know this value, we'll go parallel to this line. So our stiffness is 2 into 10 power 8. Look again, we have a frequency or time of loading that is given to you. We have joined with the temperature difference and extend the line upward towards this graph. From the given data, we also calculated penetration index, and we just have to perpendicularly, make a perpendicular from this calculated penetration, and we'll meet at this point. So whatever point we meet, we'll go parallel to this line to get the value of stiffness modulus of bitumen. Once we do that, what you are going to do, we use these properties of bituminous mix. Obviously, this we do while evaluating optimum asphalt content, and all those things are known. And we are interested in knowing the volume of the bitumen. We also know the volume of the air void, and consequently, we also, with all those things, we can know the volume of the of our graded mix as well. So knowing this value, this value will be used to know the will be used to calculate, and it's very important to calculate the stiffness of the mixture. So again, from this x-axis, we have been given, we know this stiffness of bitumen that we have calculated. We project it to the volume of bitumen, and wherever we got this volume of bitumen, 5, 10, 20, 30, we'll go perpendicular. And this is the mineral volume of aggregate, void in aggregate or mineral aggregate proportion in the mix that we have designed. And once you have got this thing, you go this perpendicular to get the value of the bituminous mix. So just we always go from, we draw a perpendicular to know the volume of bitumen that we have determined from the previous slide. Once you do that, we go perpendicular to arrive at VG that we also have calculated during the slide, and then we go for the stiffness modulus of mixture. This is one to 10. So that ends our lectures on material characterization for this course. We'll have another chapter in the next slide, in the next outing. Thank you very much for listening.